Sal and 3 friends, and they plan to bowl 1 or 2 games each. Probably after they bowl the first game, they decide if they want to bowl a second game, and the game costs $2.50. So the independent variable would be what? What would the independent quantity be? What would that be talking about? Jillian? Yeah, so this would be the total number of games. Because the amount that it's going to cost depends on if you play 1 game or 2 games. So when you're thinking about independent and dependent, you think, well, what depends on the other thing? Well, the amount of money that you're paying depends on you playing 1 game or 2 games. So the total cost would be the dependent variable. Cost depends on how many games you play. Or it depends on something else that you buy. So it says find a reasonable domain and range for these values. Well, if Sal and 3 friends plan to play 1 game or bowl 1 game or 2 games, how many games, if they were bowling, would you be playing? Or how many would you really be paying for? 4. So you're paying for either 4 games because all of them are playing. Each of them has to pay a cost of $2.50 for the game that they play. So really, you're paying for 4 games. If they decide to all play 2 games, then it would be 8. But they're either deciding they're going to all play 1, they're all going to play 2. But that's a total of 4 games versus 8 games. And they would go in the little braces because there aren't values in between them. So they're either playing 4 or they're playing 8 games. They can't play 4.5 or 5.5 or 6.5 or 6 3/4. So the range then would be the cost for 4 games versus the cost for 8 games. And 4 times $2.50 would be $10. And 8 times $2.50 would be $20. And you can't really write that as an inequality because it isn't an inequality. It doesn't go from one number connected and hitting all the values in between up to the max value. Whereas with miles and gas, yes, you could drive 54.29 miles, or you could have 10.15 gallons of gas in your tank. But when you're paying for something that has just one specific cost and that cost isn't changing, it's $2.50, you're either paying the $10 or the $20, depending on if you pay 1, you each play 1 game, or you each bowl, I should say, bowl 2 games. Questions? So independent, the dependent variable literally depends or is controlled by that variable. So whatever happens with the number of games, that actually affects the cost. Any questions? So just looking at your graphs, I literally just drew very quickly a couple of sketches. I didn't really plot points. So here are my first 2 graphs. Actually, this guy should go up here to 2. But so it first says degree. The degree is the power of the polynomial. So that's what we talked about in chapter 5. This degree is 2. The domain would be negative infinity to infinity. And the range starts at 2 and it goes up to infinity. 2 is the lowest point on the graph. For number 2, the degree, the power of x is a 1. The domain would be negative infinity to infinity, and the range is negative infinity to infinity. So here we have even versus odd. Our goal is to be able to kind of look at an even graph versus an odd graph and generalize what's going on with them. So underneath, Number 3 has a negative in front, so that's why it flipped down. Its degree was 2, which is even. The domain is still negative infinity to infinity. But the range now is kind of the opposite of the range above. It starts at negative infinity and it goes up to 4. So this number here tells us the highest value in the graph, which is also the highest value of the range. And then number 4, the power is a 3, which is an odd power. This domain is negative infinity to infinity, and the range is negative infinity to infinity. So before you flip, and I heard a lot of you flip, if you just compare those two, so the two on the left are even, the two on the right are odd, what could you say about both those odd graphs? Julian?
Both the domain and the range go from negative infinity.
Exactly. Every odd-powered graph, the domain and range will go from negative infinity to positive infinity. So both odd powers have a domain and range of negative infinity to positive infinity. Whatever the power is, as long as it's odd. So you could have a power of 5, you could have a power of 11, you could have a power of 101. As long as it's an odd power, the domain and range will always be negative infinity to positive infinity. Looking at the even ones, the domain is still negative infinity to positive infinity. So both of these have a domain of negative infinity to positive infinity. However, the range goes or uses the max or the min value. So if it's a min, it starts at the min and goes to infinity. If it's a max, it goes from negative infinity to the max. And I'm going to skip the two graphs at the bottom just to kind of save some time here. But at the very bottom, I wanted you to compare odd versus even, and we'll summarize this in your notes as well. So an odd domain is always negative infinity to infinity. The range, bless you, is always negative infinity to infinity, as long as the power is odd. And that's the largest number that you see. That's that leading coefficient. The largest power is the degree. Again, if it's even, the domain is still negative infinity to infinity. But the range would be negative infinity to the max, with the max being included, or it could be the min to positive infinity. It just depends what graph you have. So the goal would be to not use a calculator and to just look at the numbers in the equation and be able to create a domain and a range from that. And that's what we're going to try and do today. So in that little packet that I gave you yesterday, we're going to graph 4 more equations on the calculator. And then after those 4, we will pretty much be able to look at almost any equation and describe the domain or the range of the equation. So you need your calculator for 4 more problems. So we're going to make a quick little sketch again. So the first one, now we're looking at a square root graph, just to see what happens with a square root graph. So those first 6 graphs that I had you graph are all positive exponents. They're all polynomials. So now what happens if we have a square root graph? And by the end of this chapter, we'll be graphing square root graphs on our own, kind of understanding what all of the pieces do to the graph. So we have the square root of x minus 2. And when you plug that in your calculator, can anybody give me like an air drawing of what that looks like? Connor, can you kind of just give me an idea of what the square root of x minus 2 looks like? Yeah, and it's going to start at the value of 2 on the x-axis. Then it's like a hook. So it kind of just hooks in one direction. And this one hooks in the positive direction. So underneath it, it just wants you to give the domain So the domain would be wherever it's starting on the x-axis, which is 2, and then it goes to infinity. Now it just asks for the domain. That's it. So domain 2 to positive infinity. So if you graph the second one, the key thing is to kind of look to see where it is on the x-axis. So when you're graphing it, look to see where does it sit on the x-axis, so it's the x-intercept, and then just graph a general shape. Odette, do you have number 2 graphed? Where does it start on the x-axis? At -3. And then, how would it go?
Down.
Yeah, so it's going down instead of the one on the left side here, so it's kind of flipped, it reflected. And that's because of the negative sign in front. So a negative sign always makes a graph go down. When we did parabolas, a positive parabola went up, a negative parabola flipped it down. And that happens with all graphs. So a negative flips it down, no matter what the shape. So that starts at -3. So Odette, you would say then the domain is? Yeah, -3, because that's where it starts on the x-axis, to infinity. So just using those two, I could see that the domain for a square root graph uses the number underneath the radical, and we'll talk about how to solve for that, but they go to infinity. The next two are a little different. So when you graph this or plot it in your calculator, put parentheses around that denominator. So you're doing 1 divided by and then parentheses, because the calculator has to know that that x minus 5 is all together in the denominator. And that's the only way it knows that, is if you group it together. This one's a little different looking. So this one should have 2 pieces to it. And it kind of skims and then like all of a sudden just goes vertical. And then you have that same piece kind of doing the opposite. Does it look like this or do I have it flipped? I have it flipped. Here we go. So the domain for the piece on the left and then the domain for the piece on the right. You're going to have 2 domains. So the one on the left would be from -infinity. Anybody know what x value that it's getting really, really close to? You can use the trace button. Maybe you can just visually look to see what it looks like, the x number that it's getting really, really close to, like when it kind of starts to like move down or move up. Abby?
5.
Yeah, so it's getting really close to 5. That would be the x value. It's not going to touch 5, but it's going to get really, really close to it. So it gets parentheses. And then this side kind of hops over the number 5. And then it goes all the way to infinity because this here is going to infinity. It's stretching forever to the right. So essentially, my graph is like skipping over the number 5. So it's going from -infinity, but at 5, it stops. And then the other part of the graph hops over 5 and goes to positive infinity. Why is that number 5 important? Look at the bottom of the fraction. Why would 5 be important with the bottom of the fraction? What happens if you have a 5 in for x on the bottom of the fraction? Yeah, so this number here kind of tells us that. But if you plug a 5 in for x, what happens if you have 5 minus 5 in the denominator?
Zero.
It becomes 0, and you can't have a 0 in the denominator. It's not allowed to happen. So that's why it's like hopping over the number 5, because it's not allowed to be 5. You can't have a 0 in the denominator. And then if you look at the last one, graphing this, you have to put the top in parentheses and the bottom in parentheses. So once we really start graphing, you'll see that like parentheses are so important when you're trying to use the calculator. So parentheses around all of the top, parentheses around all of the bottom. I have an old school calculator. My calculator actually draws the line that it can't be, which is kind of nice because then you can see visually what that line is. But for some reason they didn't like that and they took that out of the new calculators. Mine's really old. But this line is the line that x can't be, and that x value is right now at -2. So I can see that line in my calculator, whereas yours just kind of skims along there, but you don't actually physically see the line. So this graph looks something like this. So it would be from -infinity to -2, and then from -2 to infinity. So on the next page, we're going to see if we can try and make some rules about domain. So that we can try and just look at equations and figure out what a domain is. And that would be kind of pulling out all these graphs together. So there are two cases above that it said, and this is just domain. So this is not range, this is just for the domain. It says domain excludes values that. So the one thing that it excludes a value is that it excludes values that make square roots negative. Because you can't take the square root of a negative number. So that means any number that makes a square root negative has to be excluded from the domain. Whatever's underneath here, we're going to set that equal to 0. To find that value. Sometimes it's really easy to see, but other times it isn't. If we set that equal to 0, or greater than or equal to 0, then we'll be able to find out what that number is. The second thing that domain excludes would be values that make the denominator 0. So if I have 1 over x minus 3, if I set this equal to 0 and solve, then I can find out what that special number is that makes the denominator 0. So we're just focusing on domain right now. So a square root, you can't have a negative underneath the square root. A fraction, you can't have a 0 in the denominator. Those are two restrictions that we say are happening with the domain. The other part underneath that says the domain of common functions, this is what we did. There we go. On the little warm-up. So if you have an even degree, what would the domain be of every even degree? So x squared, x to the 4th, x to the 8th, x to the 100. What's the domain of that number? Yeah, -infinity to positive infinity. Every even degree polynomial has that domain. So what happens if it's an odd degree? So just an x, like y equals x cubed, y equals x to the 5th, y equals x to the 7th. What's the domain of that, Julia? Also -infinity to positive infinity. So essentially, if it's a polynomial, meaning it has a whole number exponent, then the domain is -infinity to positive infinity. The last one here, kind of going back to chapter 1, What about absolute value functions? They're not a polynomial. Anybody remember what an absolute value function looks like? Julia, do you remember? It is a v. An absolute value function is a v. We did that back in chapter 1. So this is kind of good for us to kind of think about those functions that we've looked at so far this year. So Julia, what do you think the domain of an absolute value function would be? Negative infinity to positive infinity. So down below are functions. We're going to try and use these rules that you have above as a reference. And there are 6 functions that we're just finding the domain of. So not the range, because sometimes the range is tweaked a little bit. And we need to kind of rely on what the graph looks like. But our goal is to do these without plugging it in the calculator. So it says find the domain of the following functions without using the graph as the function of an a. Write it in interval notation. So the first thing is we have to look and decide what type of function we're dealing with. Right away, I see this as a fraction. So when it's a fraction, if you look at the top, if it makes the denominator 0, that number is excluded from the domain, meaning that's the number that the domain cannot be. The way we can easily find that is by taking the denominator and setting it equal to 0. So we have negative 7 divided by x plus 6. Well, the negative 7 doesn't matter with the domain. It's the part where the x plus 6 is going on. So if we set that equal to 0 and solve the little equation for x, Maddie, what do you get when you have x plus 6 equals 0? What's x equal? Say again?
6.
How would you take 6 to the other side?
Oh, sorry.
How do you solve for x? Huh? How do you move it over? Yeah, subtract 6. Sorry. Did you say that and I just didn't hear you? Probably 50. It's okay. So the number that is excluded is negative 6. So this means that x is not allowed to be negative 6. That's the excluded value. It's excluded because if it was 6, negative 6 plus 6 is 0, and you can't have a 0 in the denominator. So after you figure out that number, to get the domain, it goes from negative 6 up until that number. How about negative infinity up until that number? But it can't be negative 6. That's why we put a parenthesis around it. Can't speak apparently. And then the other part of the domain is going to be from negative 6 to infinity. So when we say a number is excluded, it actually requires 2 sets of parentheses because it's going to go from the left side of negative infinity up until that number, and then literally it hops over it. And this is the only way that we can show that it skips a number. So it goes from negative infinity up until it skips over it, goes right past negative 6, and then to positive infinity. So you always have 2 values when you have a fraction, and that's the way we can kind of show those 2 values. The next one, we have 3x squared minus x minus 4. What type of function is this? So look at the top options. Connor, what type of function is it?
Even degree polynomial.
Yeah, so this is an even degree polynomial. So I'll put even poly. Connor, if it's an even degree polynomial, what's the domain?
Negative infinity to positive.
Right, negative infinity to positive infinity. And that's it. Because it's a polynomial and it has an even power, no matter what, the domain is negative infinity to positive infinity. So not a lot of work, but it's more like mentally thinking. What type of function do you have? How is that happening or affecting the domain? So number 3, we have a square root. Whatever's underneath the square root has to be positive. If it's negative, then it can't exist in the domain or it has to be excluded. So an easy way to find that value is to take the numbers underneath the square root, and I'm going to say set it equal to or greater than or equal to 0 because then we know that it has to be larger than this value. So it can't be negative, and if it can't be negative, that means it could be 0 or it could be greater than or equal to 0. And then solve for that little equation. So get x by itself. So Mackenzie Myers, if you get x by itself, you would end up having x is greater than or equal to 5 halves. So if there's a square root, whatever's underneath the square root has to be positive. To show something's positive, we can set it greater than or equal to 0. How would you write this then as an interval? So this is an inequality, but we want to write it as an interval. How would you write that as an interval? Maggie, do you know how you write it as an interval? It says x is greater than or equal to 5 halves. Anyone want to take a shot at how you'd write that as an interval? Interval notation? Tushal? Say it again. Put it in a bracket. So put it in a bracket. And then what number does it go to if it's greater than or equal to 5 halves? Infinity. And that goes in a parenthesis. So greater than or equal to, it's allowed to be 5 halves. That's its starting point, but it has to be bigger than that. So in an interval, here's where it starts. And then to show it goes bigger, we say it goes to positive infinity. Questions?
Should you leave it as a fraction?
Yes,
Leave it
yes.
as a fraction?
Leave it as a fraction. If you wanted to put it as 2.5 because that's an exact fraction, but I'd say just leave it as a fraction. So if you look underneath, here's absolute value. The domain of absolute value is negative infinity to positive infinity, and that's based off of the 3 common functions that are above. And number 6, this is an odd poly, so that's also negative infinity to positive infinity. So most of them are going to be negative infinity to positive infinity. For number 5, this is where we have to find x because it's in the denominator. So again, you're solving for x when it's in the denominator or when it's underneath the radical. And whatever your number you get is the number it cannot be. That's the value that's excluded. That's what excluded means. It's not allowed to be part of the domain. So I have a worksheet. The front side of the worksheet is just like yesterday, where you have the graph, you're writing the domain based off the graph. The back side is where I do not want you to graph on a calculator. Use that page of notes as a reference. They're the common functions that we are looking at. Have an awesome day.